Okay folks, we're going to be doing a couple of experiments with forces, investigating forces. But remember, a force is a push or a pull, yeah?
And as you've already heard, force is measured in newtons, and the size of a force can be measured with a Newton balance or a spring balance.
And we're going to be spending a wee bit of time using these vehicles that are moving on this straight track here. Most important thing really to emphasise just now is the difference between balanced forces and unbalanced forces. Newton wrote down in his first law, an object will remain at rest unless acted upon by an unbalanced force. Although he actually said a wee bit more than that. He said an object will remain at rest, or if it's already moving, it will continue to move at a steady speed in a straight line unless acted upon by an unbalanced force. This object here is stationary. It's stationary because there's no unbalanced forces acting on it. There are forces acting on it. It's got its weight downwards, but its weight downwards is being supported by the upwards force of the track supporting it, and those forces are balanced.
Here's some examples of balanced forces. That boat is floating, it's stationary because the weight of the boat downwards is balanced by the upthrust, the upwards force of the water upwards, and those forces are equal and opposite. And those two cats sitting on a seesaw, they are exerting the same force downwards, they've got the same weight, and they're sitting at the same distance away from the middle of the seesaw, and the forces are balanced. Here's a slightly trickier example of an aeroplane flying at a steady speed at a constant height. Its weight downwards has to be balanced by the lift force upwards, and as it moves through the air's trying to slow it down. There's a drag force on it. More about that in a little while, but it has to maintain a forward thrust force to keep moving at a steady speed. So the vertical and the horizontal forces are balanced for steady speed at constant height. Here's another one. If you're on your bike and you want to pedal forwards at a steady speed, then your forward force must be equal to the air resistance or the drag that's acting backwards on you. So if the friction or the drag force was 15 newtons, then you have to pedal forwards with 15 newtons to stay at a steady speed. A lot of people think you need a bigger force to keep you going forward. No. If your forward force, if your driving force was bigger than 15, then the bike would speed up. If your driving force was less than 15, the bike would slow down. So if you want to go at steady speed, the forces have to be balanced. Yes, you would need a bigger force to get you moving, or you would need a bigger backwards force to stop you moving, but at a steady speed, the forces are balanced.
So sometimes you've always got to be thinking about the whole system and all the forces that are acting. So weight always acts down, and if an object isn't moving, it means there's a reaction force. There's a force in the opposite direction to that that's supporting the object, and in this case, the reaction force is the supporting force of the track. Now, if I push that wee vehicle, it doesn't go very far before it stops again. Now, there's an unbalanced force then acting on it that makes it stop, and that unbalanced force is friction. If there was no friction on this track, then if I gave that vehicle a push, then, just like what Newton said in his first law, if an object is already moving, it will continue to move at a steady speed in a straight line until it's acted upon by an unbalanced force. So the reason that vehicle doesn't keep moving is because there is an unbalanced force acting on it. We call that friction, which causes it to decelerate and stop.
Now, sometimes friction is useful, sometimes it's not useful. Friction's a force that opposes motion, and it produces heat energy. Now, when friction is useful, would be things like the soles in your shoes, or the brakes in your bike or a car, football studs giving you grip, rubber tyres on the car, carpets on your floor. They're all examples of where friction is useful, where you don't want to be slipping and sliding about the place. But there's other times where friction is not useful. For example, if you want to move very quickly through the air or through the water, so you want to cut down on air resistance, you want to reduce the drag on your car or your plane or your boat, Or you want to reduce the surface friction if you're sliding down a flume or a chute, because you don't want to end up with friction burns. So you can reduce friction by streamlining the body shape of your vehicle, or by lubricating, putting oil in your engine parts, or by removing the air that your vehicle is travelling through, or by getting your vehicle to float on a cushion of air, like an air hockey table. And that's what we're going to do in this experiment, because friction's a pain in the neck and we want to get rid of friction.
How do we get rid of the friction? We have this guy here. That guy there is called the bin. The bin blows air through the track, and as you see there's little holes all the way along it, and those holes will blow air up and make that little vehicle float. Let's turn it on. Well, it's already moving. It's already moving because that vehicle's already moving because the track isn't flat. So what I should really do before we start is get this track flat just by adjusting the level of it. Let's see how that is. Okay, so if I just hold that, let it go, still moving to the right a wee bit, a wee screw here. That's not bad. Okay, that's about right. That's about flat. So that if I was to give that vehicle a push, then it would keep going at a steady speed in a straight line because there's no unbalanced forces acting on it. We've got rid of the friction. Let's try it. Ready? Steady speed, straight line. And it'll keep going at a steady speed in a straight line until an unbalanced force acts on it. And that would be the end of the track.
Now, there's a new design for a transport system that reduces friction. It's called the Hyperloop. It's like a train that moves through a tunnel and all the air's been sucked out of the tunnel, so there's no air resistance, and it floats on a cushion. Not a cushion of air, but a cushion, a magnetic cushion, magnetic levitation. And once you get this train up to about 400 kilometres an hour, because there's no air resistance, you can just turn off the electric motor and it keeps moving at a steady speed in a straight line until it gets to wherever it needs to get to, and then you can put the brakes on and bring it to rest. It's called the Hyperloop, developed by Elon Musk, but he's too busy with space rockets and his Tesla electric cars, so it's now Richard Branson and Virgin that have taken it on, and they're developing the Hyperloop in the UK. You could maybe Google that, find out a wee bit more about it. So that's really the first thing to talk about, is that if there's no unbalanced force, if the forces are balanced, then an object will remain at rest, or if it's already moving, it will continue moving at a steady speed in a straight line. Here it is again. So give it a wee push at this end, steady speed, straight line. Once it's left my hand, once that trolley has left my hand, it just keeps moving at a steady speed in a straight line because the forces on it are balanced. Your next question is, what happens then if there's an unbalanced force acting on it? What happens if we attach something to the trolley? What happens if we attach a piece of string to the trolley? Right? So here I've got a trolley. It's got a bit of string attached to it. That bit of string is attached to a little weight, and we're going to hang the weight over the end of the track. I'll show you that at this end. So we've got our vehicle set up with a little double card on it, and the reason for the double card is when it goes through that light gate, and the light gate's connected to the TSA computer. I've got that TSA computer set up to measure acceleration. Now that vehicle's going to accelerate through the light gate because it's attached with a piece of string, and that piece of string is connected to a little hanging mass. Now, what's supporting that mass just now is the fact that that trolley, that little vehicle, is sitting on the track, and there's friction between the vehicle and the track. If I turn that air on, then we're going to get rid of the friction. We're going to blow air up through the little holes. The vehicle is going to float. We get rid of the friction,
And if there's no friction holding the vehicle, it means that that little mass, the weight of that little mass is going to pull it and it's going to accelerate through the light gate. And we're going to measure it on there. Yeah, it's weight. Let's just show you that. So just now, the forces are balanced because that's stationary. And the reason the forces are balanced is because that little hanging mass is being held in position by the friction on the track. If we get rid of the friction, watch. That vehicle accelerates through the light gate and we'll get a reading on the TSA. Now what we're going to do then is we're going to change the mass that's hanging on that string. We're going to put various masses hanging on that little mass carrier there, and from the different weights we're going to measure the different accelerations of the vehicle and we'll see how we get on. Right, here's the setup. We're going to investigate how the unbalanced force affects the acceleration of our mass here. So we're going to hang different masses onto the mass carrier, measure the weight of those hanging masses, and measure the acceleration of the vehicle. Now, if you remember from our work on pressure, remember the weight of an object is its mass times gravity here on Earth. Gravity on Earth is 9.8. So if you know what the mass is in kilograms, multiply that by 9.8 and you'll get the weight in newtons. And we are going to consider that the weight of the hanging mass is going to be the unbalanced force that's acting on the vehicle. So, there's our apparatus. Whatever our hanging mass's weight is, and once we turn the air on, it will be the weight of that mass that's providing the unbalanced force to accelerate the vehicle through the light gate. Now, there's a slight added complication here. The mass of the vehicle is 377 grams. The total hanging mass that we're going to be using is 100 grams. So we have to make sure that we keep that constant throughout the experiment. The total mass that's going to be moving is the mass of the vehicle plus the mass of the hanging mass. Now, to keep that constant, if I've only got 20 grams there just now, I need to keep the rest of the mass that I'm going to be using. I've stuck it on the end of the vehicle. So my other 80 grams is on the end of the vehicle just now. And all that means is we're keeping the mass of the moving system constant throughout the whole experiment. So it's not just the mass of the vehicle, it's the total mass that's moving, 0.477 kilograms. So we're going to put 20 grams on it, measure the weight of that, and then measure the acceleration. Right, there's my weight. Now, I'm rounding G. We know G is 9.8, but let's round it to 10 so that our weights are approximately rounded to 10 times what the mass is. And let's start measuring our acceleration. So first things first, 20 grams on the hanging mass. And it's there. Let's go. Let's measure the acceleration. There's our first acceleration then, 0.25 metres per second squared. Let's put that on the table. When the weight was 0.2 newtons, the acceleration was 0.25 metres per second squared. Let's repeat that for 40 grams. So 40 grams now on the mass carrier. Let's switch the bin on. Greater acceleration, 0.6 metres per second squared. 60 grams. We're waiting. 0.96. So as the mass goes up, the weight goes up, the acceleration goes up. Let's keep going. 80 grams. We're waiting. Blimey. 1.19. Right, finally the full 100 grams is on there. That's about 1 newton of unbalanced force. Are we waiting? I'll press waiting. Here we go. 1.59. There's our results then. Let's go and draw a graph. See what they look like.
Right, I've put all my results into a table in Excel. I have my first column is the weight of the masses, and my second column is the acceleration of the vehicle for each of those weights. Now, if we look at the graph, I've asked Excel to draw a graph of force along the bottom and acceleration on the y-axis. It's a straight line through the origin, so the unbalanced force varies directly with the acceleration. We can write that like this: the unbalanced force varies directly with the acceleration, or you could say the unbalanced force is directly proportional to the acceleration, and therefore introducing a constant. Unbalanced force is some constant times the acceleration, and rearranging F over A equals a constant. It's a constant gradient on the graph, so F divided by A is a constant. Now, Newton discovered that F over A is equal to the mass of the moving object. If we rearrange that, we get F equals ma. And F equals ma is, well, that relationship's on your relationship sheet. But that relationship, F equals ma, is sometimes called Newton's second law. The unbalanced force equals the mass times the acceleration of the object. That should be meters per second squared. So F equals ma is often called Newton's second law. It's the most important equation that we use when we're doing calculations on moving objects that are accelerating. So if your mass is constant, you're going to need twice the force to get twice the acceleration. They're directly proportional. If your force is constant, then with a bigger mass, you're going to get a smaller acceleration. So they are inversely proportional. And for a constant acceleration, then you'll need a bigger force if you've got a bigger mass. All three of those relationships can be seen if we put Newton's second law into a triangle. F at the top, ma on the bottom, so F equals ma. And the one thing we probably haven't mentioned so far is, what about friction? Well, we got rid of friction with our linear air track, and friction is often removed from any of the examples that you will do. That just makes life easier for you. But if friction is included and it is present, then you will have to take that into consideration when you're doing any calculations. So let's try a couple, an easy one and then one that includes friction as well. So here's a car. That car is driving along a flat road. It's got a mass of 1,200 kilograms and it is accelerating. So we need a driving force. Now the engine produces that unbalanced force then, and let's just say that that engine force is 4,200 newtons, and we have to calculate the acceleration of the car. Well, we use our Newton's second law relationship, F equals ma. Don't forget, draw a little triangle, put the equation in a triangle if you want. F is at the top, ma at the bottom, and we are looking for the acceleration. So A equals F over m. Well, let's just substitute the numbers in. So the unbalanced force was 4,200 and the mass of the car 1,200 kilograms. That gives us an answer of 3.5 meters per second squared. And you will notice there's no friction, no mention of friction in that question. The only force we had was the driving force of 4,200 newtons. And that is about as easy as an example as you will see. It gets a wee bit trickier when friction is included. So no friction in that example. But let's now include friction. Let's do exactly the same question. So the car is accelerating along the road. Same engine force, but this time friction is included. Let's say that there is a frictional force of 600 newtons. Now, that might be road friction at the tyres, or it might be air resistance. What will the acceleration of the car be this time? It's the same equation, A equals F over M, but what are we going to put in for our unbalanced force? Well, the unbalanced force is the result of all the different forces that are acting on the car. So there's 4,200 newtons forwards, there is 600 newtons of friction. Friction always opposes the motion of your car, so it's always acting backwards. So the unbalanced force is the difference between the two. That's 3,600 newtons to the right. So that's what we put in for our unbalanced force, 3,600 divided by the mass of the car, 1,200 kilograms, gives us an answer this time of only 3 meters per second squared. So the acceleration is less. It's smaller if we take friction into account. Okay, let's try lots of examples. It's fun, you know. Fun equals MA. See you in the next one.